13.8 billion years. Trillions of galaxies, massive black holes, and 93 billion light years of infinite space. The iron in your blood and the calcium in your bones were forged in the hearts of dying stars billions of years ago. Your very existence is tied to the epic story of the universe, from the first quark to the last human thought. But what happened in between? How did we get from nothing to everything? Imagine a state of absolute nothingness. No space, no time, no matter, no energy. This was the before of our universe. Then, in an instant, everything changed. The Big Bang erupted, marking the explosive birth of our cosmos. In this moment of creation, an unimaginable amount of energy surged forth, initiating a rapid expansion that continues to this day. In the earliest moments, the universe was an inferno of pure energy, too hot for even subatomic particles to exist. As it expanded, it began to cool. This cooling allowed for the formation of the first subatomic particles, the building blocks of all matter. These particles, born in the furnace of creation, would eventually combine to form everything we see around us. But what happened next would lay the foundation for everything we see today. As the universe's fiery inferno began to cool, something incredible began to happen. A cosmic transformation that would shape the very fabric of our reality. In the first moments after the Big Bang, the universe was an unimaginably hot and dense soup of energy. As it expanded and cooled, the stage was set for the formation of the first subatomic particles. Quarks and electrons would lead to the creation of protons and neutrons. These fundamental particles would become the building blocks of all matter. Within the first few minutes after the Big Bang, a process called nucleosynthesis began, combining protons and neutrons to form the nuclei of the first elements, a universe composed of approximately 75% hydrogen and 25% helium with trace amounts of lithium. Deuterium nuclei formed first, eventually fusing into helium. But the conditions had to be just right. If the universe had cooled too quickly or too slowly, the process would have been disrupted, potentially changing the course of the universe. These first elements, simple as they were, laid the foundation for everything that was to come. Hydrogen and helium would later fuel the first stars, starting the cycle of stellar evolution that would eventually produce all the heavier elements we know today. However, before stars could form, the universe had to go through another transformation. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with nuclei, forming the first stable atoms. This moment, known as recombination, marked a significant milestone in the universe's history. With the formation of stable atoms, the universe suddenly became transparent to light. The energy that had been trapped by free electrons was now free to travel across the cosmos. This released energy is what we now observe as the cosmic microwave background radiation. The slight temperature variations in this radiation reveal the density fluctuations that would eventually lead to the formation of galaxies and large-scale structures in the universe. Shortly after recombination, as the first molecules began to form, the universe entered a profound period of darkness for nearly 1 billion years, called the Dark Ages. During this time, the universe continued to expand, but it was without any visible light sources. Imagine a vast, ever-growing expanse of space filled with nothing but neutral hydrogen and helium atoms, drifting in complete darkness. The only photons present were those released during the earlier event of decoupling, and since then this light had stretched out into infrared wavelengths. As a result, the universe became transparent, allowing light to travel freely for the first time, but ironically there were no new sources of light to illuminate it. The matter was too evenly distributed to collapse under its own gravity and form larger structures. The universe needed time to develop the necessary density fluctuations that would eventually lead to the formation of stars and galaxies. While the visible universe remained dark, invisible forces were at work shaping its future. Dark matter, a mysterious substance that doesn't interact with light but exerts gravitational influence, played a crucial role during this period. It's believed that dark matter formed gravitational centers that slowly attracted visible matter, creating the seeds for future cosmic structures. The end of the Dark Ages were marked by a process called reionization. This is when the first stars and galaxies started to form. These stars, known as population 3 stars, were unlike anything we see in our night sky today. They began to create heavier elements in their cores with masses potentially hundreds of times greater than our Sun, and created the perfect conditions for nuclear fusion. However, the lives of these stars were remarkably brief. While stars like our Sun can burn for billions of years, population 3 stars existed for only a few million years. Their immense size and the intensity of their nuclear reactions led to a rapid consumption of their fuel, which ended in colossal explosions known as supernovae, events so powerful that they briefly outshone entire galaxies and created most of the everyday elements we see around us today. The explosion scattered newly forged elements like carbon, oxygen, and iron into the surrounding space. These heavier elements, absent in the early universe, would become the building blocks for future stars, planets, and eventually life itself. The supernovae of population 3 stars marked a turning point in the evolution of our universe. They filled the space between stars with metals or any element heavier than helium. This new, more complex chemistry allowed for the formation of smaller, longer-lived stars and facilitated the eventual emergence of planets and complex molecules necessary for life. While we have yet to directly observe a population 3 star, their existence and characteristics are inferred from complex computer simulations and observations of later star generations. The oldest stars we can see today, known as population 2 stars, bear the chemical signatures of earlier stellar generations, providing indirect evidence of their population 3 predecessors. The era of the first stars also witnessed the birth of the first galaxies. As these massive stars exploded, their remains, along with surrounding gas and dark matter, began to combine under the influence of gravity. These early galaxies were probably small and irregular compared to the beautiful spiral and elliptical galaxies we see today, but they laid the groundwork for the massive structures that now fill our universe. The process of galaxy formation began approximately 400 million years after the Big Bang, as gravity caused gas and dust to combine into larger structures. However, visible matter alone couldn't account for the complex structure of the universe we see today. Enter dark matter. Dark matter, which constitutes about 84.5% of the matter content in the universe, provided the gravitational scaffold around which visible matter could cluster. This mysterious substance, which doesn't interact with light but exerts gravitational influence, formed a cosmic web of filaments and halos that guided the formation of galaxies and clusters. The distribution of galaxies in the universe is far from random. The universe is mostly the same everywhere we look, but small differences in density exist. These tiny variations became the seeds that grew into everything we see today. Our own galaxy, the Milky Way, began to take shape around 13.6 billion years ago, shortly after the first stars formed. Its formation was a complex process involving the merging of smaller galaxies and the accumulation of gas and dust. Over billions of years, these gravitational interactions sculpted the spiral structure we see today. Throughout the universe, gravitational interactions between galaxies led to the formation of even larger structures. Galaxy clusters and superclusters emerged, creating the largest known structures in the cosmos. But these galactic interactions are still ongoing. Our own Milky Way, for instance, is on a collision course with the neighboring Andromeda galaxy. In about 4 billion years, these two spiral galaxies will merge, creating a new, larger elliptical galaxy. Furthermore, each type of galaxy tells a unique story of formation and evolution. Spiral galaxies are often sites of active star formation, while elliptical galaxies are generally older with less ongoing star formation. Irregular galaxies, on the other hand, are often the result of gravitational interactions or mergers between other galaxies, and within these chaotic structures lie billions of stars and planets, some perhaps like our own. Approximately 4.6 billion years ago, in a quiet corner of the Milky Way, a solar nebula began to collapse under its own gravity. This cloud of gas and dust, composed of material from previous generations of stars, contained the seeds of our entire solar system. As it contracted, the nebula began to spin faster, flattening into a disk with a dense center. The majority of the material in this primordial disk fell towards the center, growing hotter and denser until nuclear fusion ignited, giving birth to our Sun. The remaining material began to clump together through a process called accretion. These growing clumps became the planets, moons, asteroids, and comets that now orbit our star. The formation of the planets was a chaotic process. In the inner solar system, rocky materials combined to form the terrestrial planets: Mercury, Venus, Earth, and Mars. Further out, where temperatures were cooler, gas giants like Jupiter and Saturn formed, their massive gravitational pull allowing them to accumulate vast amounts of hydrogen and helium. Earth's formation was particularly eventful. As it grew, our planet experienced a cataclysmic collision with a Mars-sized body named Theia. This massive impact not only contributed to Earth's final mass, but also resulted in the formation of our moon. The moon's creation stabilized our planet's axial tilt and influenced its rotational dynamics. The early solar system was a chaotic place, characterized by a period known as the Late Heavy Bombardment. During this time, Earth and the other inner planets were hit by an intense barrage of asteroids and comets for several 100 million years. On Earth, the impacts delivered water and other essential materials to our planet's surface. The origin of Earth's water has been a subject of debate among scientists, with evidence suggesting a combination of sources. Some water likely came from the outgassing of the planet's interior through volcanic activity, while a significant portion is believed to have been delivered by icy bodies during the bombardment phase. As Earth cooled, its atmosphere began to form. Initially composed mainly of carbon dioxide, nitrogen, and steam, the early Earth was a molten landscape. Over time, as the planet's surface temperature decreased, water began to condense, forming the first oceans. These bodies of water would prove critical for the emergence of life. Early Earth was a world of extremes, with intense volcanic activity contributing to the cycling of nutrients and the further development of the atmosphere. This volcanic activity, combined with the presence of liquid water, created a complex chemical environment that would later prove crucial for the emergence of life. Earth's position in the solar system, often referred to as the Goldilocks zone, provided just the right conditions for liquid water to exist on its surface. This area, combined with the planet's size, composition, and the presence of a protective magnetic field, set Earth apart from other planets in our solar system and is thought to be rare in the universe. But approximately 4 billion years ago, our planet was a hostile environment with scorching temperatures and intense volcanic activity. The atmosphere, without any oxygen, consisted primarily of carbon dioxide, nitrogen, and steam. However, around 3.8 billion years ago, Earth experienced its first rainfall. As the planet cooled, water vapor condensed and fell as rain, initiating the formation of the first oceans. In addition, constant meteor bombardment contributed additional water to the growing seas. These ancient oceans became the birthplace of life. The leading theory for the origin of life suggests that it began near hydrothermal vents on the ocean floor. These underwater fissures, spewing hot, mineral-rich fluids, created unique chemical and energy gradients. These extreme conditions might have sparked the creation of organic molecules through chemical reactions driven by various energy sources. Lightning strikes and volcanic activity likely played crucial roles, providing the energy needed to forge complex organic compounds from simpler molecules present in the early atmosphere and oceans. As these organic molecules gathered in Earth's early oceans, they started to interact and combine in more complex ways. Over time, through countless chemical reactions and interactions, the first self-replicating molecules emerged. The first living organisms on Earth were likely simple, single-celled prokaryotes. They lacked a nucleus and other complex cellular structures found in modern organisms, but they did have the ability to metabolize energy, grow, and reproduce. These early organisms faced many challenges in their tough environment. They had to find ways to keep their internal chemistry stable, get energy from their surroundings, and protect themselves from environmental threats. Interestingly, the first photosynthetic organisms likely absorbed infrared light rather than visible light and produced sulfur instead of oxygen. But these single-celled organisms were the ancestors of all life we see today. Approximately 600 million years ago, the world of microscopic, single-celled organisms gave way to more complex, multicellular life forms. The rise of multicellular organisms was a gradual process. These early complex life forms likely began as colonies of single cells that developed specialized functions. Over time, these specialized cells became more interdependent, leading to the emergence of true multicellular organisms with different tissues and organs. However, the evolution of complex life was linked to a monumental shift in Earth's atmosphere. Approximately 2.5 billion years ago, a group of microscopic organisms called cyanobacteria began to dramatically alter the planet's environment. These early photosynthesizers started producing oxygen as a byproduct of their metabolism, initiating what scientists call the Great Oxidation Event. The rise in atmospheric oxygen levels had profound consequences for life on Earth. Initially, oxygen was toxic to many existing life forms, causing a mass extinction among anaerobic organisms. However, the increased oxygen levels paved the way for the development of more complex, energy-intensive life forms. As oxygen levels continued to rise, the stage was set for an explosion of biological diversity. The Cambrian explosion, beginning around 541 million years ago, marked a period of rapid evolutionary innovation. During this time, almost all major animal phyla appeared in the fossil record. The oceans teemed with a variety of new life forms, including the ancestors of modern arthropods, mollusks, and vertebrates. The fossils from this time show a variety of body shapes and ways of living. Some organisms developed hard shells or exoskeletons, while others evolved more complex sensory and nervous systems. This surge in diversity laid the groundwork for the complex ecosystems we observe today. The evolution of plants played a crucial role in shaping Earth's terrestrial environments. The first land plants appeared approximately 470 million years ago, gradually transforming barren landscapes into lush, vegetated habitats. These early plants not only changed the physical landscape, but also increased oxygen levels. As plants colonized the land, they created new niches for animal life. Insects were among the first animals to make the move to living on land, followed by amphibians, reptiles, and eventually mammals and birds. Each group evolved unique adaptations to meet the challenges of life on land, from ways to conserve water to more efficient movements. The Paleozoic era witnessed the rise of fish, the first vertebrates, and their subsequent adaptation to life on land. The development of lungs and limbs in some fish lineages led to the emergence of tetrapods, the four-limbed vertebrates that would go on to dominate terrestrial ecosystems. The evolution of complex life forms is intricately linked to environmental changes. The interaction between living organisms and their environment led to the development of more advanced adaptations. For example, as predators evolved, prey species developed better defenses, creating a cycle of improvements that drove further diversity. By the beginning of the Mesozoic era, roughly 252 million years ago, the stage was set for the rise of the dinosaurs. During this time, Earth's landscape and climate were vastly different from what we know today. The planet was generally warmer with no polar ice caps. This global warmth resulted in lush vegetation and diverse ecosystems that supported an incredible array of dinosaur species. Imagine a world where dense forests stretched from pole to pole, and vast inland seas covered much of what are now continents. The supercontinent Pangaea, which had formed during the previous era, began to break apart, creating new habitats and influenced the evolution and distribution of dinosaur species across the globe. Over 700 species have been identified, ranging from small bird-like theropods to massive sauropods that stretched longer than a tennis court. Some developed complex social behaviors, others evolved elaborate defensive structures, and many showcased vibrant colors and patterns that rivaled those of modern birds. The Mesozoic saw the emergence of iconic species like the Tyrannosaurus rex, Stegosaurus, and Brachiosaurus. But dinosaurs weren't the only inhabitants of this ancient world. The Mesozoic also saw the evolution of the first mammals, the diversification of insects, and the appearance of flowering plants. For millions of years, dinosaurs dominated terrestrial ecosystems, adapting to gradual changes in climate and geography. However, their reign was met with a drastic end. Approximately 66 million years ago, a massive asteroid known as the Chicxulub impactor struck the Earth near what is now the Yucatan Peninsula in Mexico. The impact triggered worldwide wildfires, massive tsunamis, and ejected so much debris into the atmosphere that it blocked out sunlight for an extended period. This nuclear winter led to rapid cooling and changes in plant growth that rippled through the entire food chain. Approximately 75% of all plant and animal species on Earth, including all non-avian dinosaurs, went extinct. This mass extinction event marked the end of the Mesozoic era and the Cretaceous period, fundamentally altering the course of life on Earth, and opened a new chapter in Earth's history, the dawn of humanity. In the wake of the dinosaurs' extinction, small nocturnal mammals began to thrive in the newly opened ecological niches. Among these survivors were the earliest primates, emerging around 65 million years ago. These tree-dwelling creatures, with their forward-facing eyes and grasping hands, were the distant ancestors of all modern primates, including humans. Over millions of years, primates diversified and evolved, adapting to various environments. The first hominins, our earliest human-like ancestors, appeared in Africa approximately 6 million years ago. These early hominins developed a crucial adaptation that would set them on the path to humanity: bipedalism, or the ability to walk upright on two legs. Bipedalism freed the hands for tool use, allowed for more efficient movement, and may have contributed to the expansion of early hominin ranges. This adaptation also coincided with climate changes in Africa, as forests gave way to more open savannas. Over time, these early humans evolved larger brains. During the course of human evolution, brain volume nearly quadrupled, from about 350 cubic centimeters in early hominins to an average of 1,300 cubic centimeters in modern humans, which allowed for more complex problem-solving, social interactions, and eventually the development of language. The genus Homo, to which modern humans belong, first appeared around 2.5 million years ago. These early humans were characterized by larger brains, smaller teeth, and more human-like body proportions compared to their Australopithecine predecessors. It was during this time that one of the most significant milestones in human evolution occurred: the development of stone tools. The oldest known stone tools, dating back to about 3.3 million years ago, marked the beginning of human technology. These simple tools, known as the Oldowan industry, consisted of sharpened stones used for cutting and scraping. As Homo species continued to evolve, they began to spread beyond Africa. Homo erectus, one of the first human species to leave Africa, had reached Asia by about 1.8 million years ago. The development of language, while difficult to pinpoint in the fossil record, was another crucial milestone in human evolution. The ability to communicate complex ideas and share knowledge across generations allowed for unprecedented cooperation and cultural development. Language likely co-evolved with increasing brain size and social complexity, becoming more sophisticated over hundreds of thousands of years. Homo sapiens, our own species, emerged in Africa around 300,000 years ago. These early modern humans possessed cognitive abilities similar to our own, capable of abstract thought, complex planning, and artistic expression. Evidence of symbolic behavior, such as the use of ochre for body decoration and the creation of jewelry, appears in the archaeological record by at least 100,000 years ago. Around 70,000 years ago, Homo sapiens began to leave Africa in significant numbers, eventually spreading to every habitable continent ranging from Arctic tundra to tropical rainforests, and thus begins the rise of human civilization. From simple stone tools to space exploration, human ingenuity has known no bounds, but perhaps our greatest achievement was learning to harness the power of the Earth itself. Approximately 10,000 years ago, a revolution began that would forever alter the course of human history: the agricultural revolution. This transition from hunter-gatherer lifestyles to settled farming communities marked a fundamental change in how humans interacted with their environment. For the first time, our ancestors could control their food supply, cultivating crops and domesticating animals rather than relying solely on what nature provided. It allowed for population growth and the development of more complex social structures. As communities grew, specialization of labor became possible. No longer did every individual need to focus solely on obtaining food. Some could now dedicate their time to other pursuits, such as craftsmanship, trade, or governance. This shift laid the groundwork for the rise of the first cities. Urban centers emerged in fertile regions like Mesopotamia, the Nile Valley, and the Indus Valley. The concentration of people and resources in these areas accelerated the pace of human progress. As societies grew more complex, so did the technologies they developed. The invention of writing systems around 3200 BCE revolutionized human communication and record-keeping. This allowed for the preservation and transmission of knowledge across generations, a crucial factor in the advancement of science and culture. The development of metallurgy marked another significant leap forward. The ability to work with copper, bronze, and eventually iron led to improved tools and weapons, transforming agriculture, craftsmanship, and warfare. These technological advancements, in turn, facilitated the growth of trade networks and the spread of ideas across vast distances. Throughout history, human understanding of the universe has evolved dramatically. Ancient civilizations, such as the Babylonians, Egyptians, and Greeks, made significant contributions to astronomy. They mapped the stars, tracked the movements of planets, and developed sophisticated calendars. These early astronomers laid the foundation for our modern understanding of the cosmos. The scientific revolution of the 16th and 17th centuries marked a turning point in human comprehension of the universe. Figures like Copernicus, Galileo, and Newton challenged long-held beliefs about the nature of the cosmos. The heliocentric model replaced the geocentric view, and the laws of motion and gravity provided a mathematical framework for understanding the movements of celestial bodies. As our technological capabilities advanced, so did our ability to observe and study the universe. The invention of the telescope in the early 17th century opened up new views for astronomical observation. Each subsequent improvement in telescopic technology has allowed us to peer further into space and time, revealing the true vastness and complexity of the cosmos. The 20th century brought about a revolution in our understanding of the universe. Einstein's theories of special and general relativity fundamentally altered our conception of space, time, and gravity. The discovery of the expanding universe by Edwin Hubble led to the development of the Big Bang Theory, providing a framework for understanding the origin and evolution of the cosmos. And thus, we come full circle, leading us back into space. The space age, a period of rapid technological advancement and unprecedented exploration, began with a single beep heard round the world. On October 4, 1957, the Soviet Union launched Sputnik 1, the first artificial satellite to orbit Earth. This basketball-sized sphere, emitting radio pulses as it circled our planet, ignited a fierce competition between superpowers and captured the imagination of people worldwide. The launch of Sputnik 1 caused a series of remarkable achievements in space exploration. Within a few years, both the Soviet Union and the United States had sent animals into space, paving the way for human spaceflight. On April 12, 1961, Soviet cosmonaut Yuri Gagarin became the first human to journey into outer space, completing a single orbit around Earth in his Vostok 1 spacecraft. The United States quickly followed suit. On May 5, 1961, Alan Shepard became the first American in space during a suborbital flight aboard Freedom 7. These initial journeys beyond Earth's atmosphere were brief, but they demonstrated the feasibility of human spaceflight and set the stage for more ambitious missions. As the space race intensified, technological advancements accelerated at an unprecedented pace. Rocket technology improved rapidly, allowing for longer missions and heavier payloads. The development of more sophisticated life support systems enabled astronauts to spend extended periods in the harsh environment of space. The next major milestone came on July 20th, 1969, when Neil Armstrong and Buzz Aldrin became the first humans to set foot on another celestial body. As Armstrong descended the ladder of the lunar module Eagle, he uttered the now famous words, "That's one small step for man, one giant leap for mankind." This achievement, broadcast live to millions around the world, represented the culmination of years of scientific and engineering effort. The Apollo program continued with several more successful lunar missions, each expanding our knowledge of Earth's moon, from its geology, formation, and relationship to Earth. The rocks and soil samples brought back by Apollo astronauts continue to yield new insights decades later. While the moon landings captured public imagination, unmanned space probes were quietly revolutionizing our understanding of the solar system. The Mariner missions to Venus and Mars, launched in the 1960s and early 1970s, provided our first close-up views of these neighboring planets. The Pioneer and Voyager probes, launched in the 1970s, revealed the stunning diversity of the outer planets and their moons. Since then, we have ventured to every planet in our solar system, as well as numerous asteroids and comets, revealing ice volcanoes on Pluto, hydrocarbon seas on Titan, and potential subsurface oceans on several of Jupiter and Saturn's moons. Each discovery has expanded our understanding of planetary formation and the potential for life beyond Earth. But more importantly, it showed how small we really are in the universe. The observable universe, which is the portion we can see and study from Earth, spans an astonishing 93 billion light-years in diameter. It contains all the matter and energy that can be observed from our planet at the present time. However, it is just a fraction of the entire universe. Modern astronomy has revolutionized our understanding of the cosmos, revealing a universe far more complex and mysterious than previously imagined. One of the most groundbreaking discoveries of the past century is the existence of dark matter. It doesn't interact with light, but exerts gravitational influence, and is believed to make up about 27% of the universe's total mass energy content. Complementing dark matter is an even more confusing component, dark energy. Constituting approximately 68% of the universe, dark energy is the force responsible for the accelerating expansion of the cosmos. Together, dark matter and dark energy account for about 95% of the universe's content, leaving only 5% for the ordinary matter that makes up stars, planets, and living beings. This means that the universe we observe with our most powerful telescopes represents only a small fraction of what actually exists. Another key revelation in modern cosmology is the concept of cosmic inflation. Proposed by physicist Alan Guth, this theory suggests that the universe underwent a period of rapid, exponential expansion in the first moments after the Big Bang. This inflationary period helps explain several puzzling aspects of the cosmos, including its remarkable uniformity on large scales and apparently flat geometry. The cosmic microwave background is remarkably uniform, with temperature variations of only 1 part in 100,000. This uniformity presents a challenge called the horizon problem, because it suggests that areas of space that couldn't have interacted still somehow reached the same temperature, and thus formed the universe we see today. It might be 13.8 billion years old, yet on a cosmic scale, our universe is still in its infancy, with potentially trillions of years of evolution ahead, with new stars born and old ones dying every day. In our Milky Way galaxy alone, an average of 1 new star forms each year. Meanwhile, supernovae explosions mark the dramatic deaths of massive stars, enriching the space between stars with heavy elements essential for forming planets and life. As the universe expands, it becomes larger, colder, and more dilute. This ongoing expansion has profound implications for our future. Over incredibly vast timescales, all structures will eventually decompose into subatomic particles and low-energy radiation. The universe is moving towards a state of maximum entropy, a concept known as the heat death, or Big Freeze. The current understanding of the universe's expansion and its future is still evolving. Observations of distant galaxies provide a window into the past, allowing astronomers to piece together the universe's evolutionary timeline. The light from these galaxies has traveled billions of years to reach us, showing the universe at different stages of its development. This helps us understand how galaxies form and evolve over time, giving us insights into our future. The ultimate fate of the universe remains one of the most profound questions in cosmology. Current theories, based on our understanding of dark energy and the expanding universe, point towards a scenario known as the Big Freeze or heat death. In this model, the universe continues to expand indefinitely, becoming increasingly sparse and cold. As the universe expands, galaxies move farther apart, and the formation of new stars gradually ends. Over incredibly vast timescales, even the most massive stars will exhaust their fuel and fade away. Black holes, once thought to be eternal, will slowly evaporate through a process called Hawking radiation. Eventually, all structures in the universe will decompose into subatomic particles and low-energy radiation. The Big Freeze scenario paints a bleak picture of the universe's final state. Entropy, a measure of disorder in a system, reaches its maximum. In this state of maximum entropy, no work can be done, and no information can be processed. The universe becomes a vast, cold expanse of uniformly distributed particles, empty of any visible structure or energy gradients. While the Big Freeze is the most widely accepted theory for the universe's ultimate fate, it's not the only possibility. Alternative scenarios, each with its own set of implications, have been proposed by cosmologists. One such alternative is the Big Rip. In this scenario, the mysterious force of dark energy, which is currently causing the universe's expansion to accelerate, continues to grow stronger over time. Eventually, this force becomes so powerful that it overcomes all other forces, including those holding atoms and subatomic particles together. The universe quite literally tears itself apart, with even the fabric of space-time ultimately shredded. Another possibility, though considered less likely based on current observations, is the Big Crunch. In this model, the expansion of the universe eventually slows and reverses. Gravity overcomes the expansion, leading to a contraction of the universe. All matter collapses back into a singularity, potentially setting the stage for another Big Bang and a new cycle of cosmic evolution. These scenarios unfold over timescales that dwarf the current age of the universe. The Big Freeze, for instance, would occur over a period of Google years, a number so large it defies intuitive understanding. We exist in the universe's adolescence, a time of vibrant activity and growth. The stars are still shining, galaxies are still forming and evolving, and the cosmic web continues to shape itself under the influence of gravity and dark energy. From the Big Bang to the present day, our universe has undergone a remarkable evolution. The initial burst of energy gave rise to fundamental particles, which combined into atoms, stars, and galaxies that we observe today. Our very existence is linked to the universe's history. The elements that form our bodies were forged in the hearts of stars, connecting us to the cosmic processes that have shaped our universe for billions of years. As we continue to unravel the mysteries of the universe, we are, in essence, the universe becoming aware of itself. Our search for knowledge isn't just a human effort, it's the universe itself trying to understand its own nature and origins.